In this work, we demonstrate how we extended the high-fidelity aerostructural optimization framework MACH to include geometrically nonlinear finite element formulations. We also demonstrate how geometrically nonlinear phenomena affect the optimal structural sizing of high aspect ratio wings. Before continuing, I'd like to acknowledge the support I received from TU Delft during this project, both from my co-supervisor Roland de Broker and through a Justus and Louise van Effen research grant. Over the past 50 years, commercial aircraft wings have steadily grown in aspect ratio and flexibility. To a large extent, this has been driven by improvements in the computational tools we use for aerostructural analysis and design. These tools have enabled us to shift from viewing the coupling between aerodynamic and structural design as a nuisance to seeing it as a key area for exploitation. Recently, both in academia and industry, we've moved from developing tools for aerostructural analysis to tools for aerostructural optimization. Just like analysis tools, these optimization frameworks come in both low and high fidelity versions. Low fidelity tools such as Proteus, pictured here on the left, use panel-based aerodynamic models and beam finite elements. At the other end of the scale, we have the MACH framework, which represents the current state of the art in high fidelity optimization. In MACH, we use RANS CFD to model transonic aerodynamics and shell finite element wingbox models. Both these approaches have their pros and cons. Low fidelity tools obviously have much lower computational cost, and the use of beam finite element models makes it simpler to include geometrically nonlinear structural formulations required for the analysis of highly flexible wings. However, panel-based aerodynamic models can't accurately predict cruise drag, meaning these frameworks are typically limited to optimizing only structural sizing with a fixed wing shape. On the other hand, using RANS CFD allows MACH to simultaneously optimize a wing shape and structural sizing, and the use of a full wingbox model allows for more detailed structural sizing. However, the cost of these optimizations is only just becoming practical for design purposes, and, to date, MACH has only been capable of using linear finite elements. In this work, we address this issue by extending the MACH framework to include a geometrically nonlinear finite element formulation. First, I'm going to talk about the solvers we implemented for geometrically nonlinear structural and aerostructural analysis. Then we'll demonstrate those solvers in the context of analysis and optimization, and finally I'll comment a bit on computational cost. For geometrically nonlinear structural analysis, we implement a Newton-Raphson-based nonlinear solver in MACH's finite element library TACS. To make the solver robust enough for use in optimization, we implement an adaptive strategy for gradually applying loads to the structure in increments. Here you can see an example of this, where the solver is unable to converge the large initial load increments and eventually reduces the size to a level where it achieves consistent convergence in each increment. For aerostructural analysis, we use MACH's partitioned aerostructural solver. Because of the way we implemented our structural solver, no modifications were strictly necessary in order to perform nonlinear aerostructural analysis. We simply provide a nonlinear finite element model to the aerostructural solver and everything works as before. However, we were able to improve the performance of our solver by implementing the load ramping method proposed by Sanchez et al. Notice in this example how the wing on the bottom with load ramping is significantly more stable in the early iterations of the solver. In testing, we found that this additional stability could improve the solution time by up to 40%. Now we compare the results of linear and nonlinear structural analysis with identical loading on the high aspect ratio wing box of the undeflected common research model. We find that due to the correct treatment of rotated aerodynamic forces on the outer portions of the wing, the nonlinear analysis results in bending stresses 10 to 15% higher than in the linear case. We also demonstrate the presence of significant rib crushing loads in the nonlinear case, which increase the buckling failure criteria in the ribs by as much as 50%. We then compare the results of linear and nonlinear aerostructural analyses. both trimmed to the same 2.5G maneuver condition. From an aerodynamic perspective, the most notable geometrically nonlinear effect is the shortening of the effective wingspan. This causes an inboard and forward shift of the wing's center of pressure. This alters the trim of the aircraft and results in a slight reduction in the fraction of the total lift produced by the wing. From a structural perspective, we find that the bending stresses are lower this time in the nonlinear case. Rather than being the result of an increase in passive load alleviation, this reduction is most likely also due to the reduction in effective moment arm of the aerodynamic forces and in the total lift produced by the wing. We now move on to optimizing the structural design of the UCRM wing box. The first case we investigate is a pure structural optimization using the same identical fixed loads as before. We parameterize the structural design of the wing box with over 1,000 design variables. In the second case, we use coupled aerostructural analysis, allowing the optimizer to aeroelastically tailor the wing. In both cases, we apply constraints on structural failure in 2.5 and -1G maneuver conditions. The difference between linear and nonlinear structural optimization results are consistent with the differences we saw in the earlier structural analyses. In the nonlinear case, the mass is 7% higher, and most of this difference is in the upper and lower skins. For the most part, the thickness distributions in the skin are qualitatively similar between the linear and nonlinear optimized designs. The rib crushing loads we observed earlier result in a significant increase in the bending stiffness of the ribs in the nonlinear case, but the optimizer is able to achieve this with little to no mass increase. In our aerostructural optimizations, the optimizer promotes passive load alleviation by reinforcing the leading edge spar rather than the wing skins. Doing so leads to a 25% reduction in the optimized wing box mass. However, contrary to our aerostructural analysis results, the wing box optimized with geometrically nonlinear analysis is 4.5% heavier than the linear optimized designs. Currently, we believe this may be due to unrealistic stress peaks around the engine mount in the nonlinear analysis, as both wings appear to achieve similar amounts of load alleviation. Finally, given how expensive these high-fidelity optimizations are already, it's important that we quantify how much more expensive they get when we use geometrically nonlinear models. For purely structural analysis and optimization, using a geometrically nonlinear formulation does increase the cost by around an order of magnitude. However, in aerostructural analysis and optimization, the CFD remains the dominating cost, and the penalty for adding geometric nonlinearity is therefore much lower. For analysis, we have found that the cost increased by around 40 to 50%, and for optimization, it can be as low as 15%. So, to conclude, in this work, we identified a gap between low-fidelity aeroelastic optimization tools that include geometric nonlinearity and high-fidelity tools which don't. To address this gap, we extended the MACH framework to use geometrically nonlinear finite element formulations. We demonstrated that geometric nonlinearity has significant effects on the results of structural and aerostructural analysis and optimization of high aspect ratio transport aircraft wings, and finally, we showed that the computational cost of these optimizations remains practical when we add these nonlinear models. If you found this presentation interesting, I'd recommend checking out the rest of the mdolab's presentations at this year's conference. With that, I'll say thank you, and I look forward to answering your questions in the live Q&A session.